Kevin Gu. Parag, it looks like you have a fan club joining us on here.
No, we have Dr. Niels Boyson from Germany. I think Dr. Gentili knows him. I think Mina also knows him. Hi, Dr. Lowe. How are you doing?
Hey, how are you?
I'm
Hey,
good.
you ready?
Good, yeah.
We're waiting on Kevin Gu.
We also have another guest from, I think he's from Portugal. He's one of the literature I cited. He's from Portugal.
Awesome. I'm going to text Kevin.
I hope you're ready for some tough questions from my son.
Hi.
Hi. Hi. Hello, what's your name?
What's your name?
Michael.
His name's Michael. He's still learning to talk.
Oh, so cute.
I think what we ought to do is just go ahead and get going. I think Kevin Gu will join us. First of all, I'm John Usher, for those of you that don't know me, and professor of industrial engineering. I want to welcome everyone here today for the dissertation defense by our excellent student, Parag Siddique. The title of his dissertation is High Density Parking for Autonomous Vehicles. This is a project that he originally started. It was funded through the Logistics and Distribution Institute, started working with Dr. Kevin Gu, who is co-advising. Dr. Gu, of course, was a faculty member here and director of the Logistics and Distribution Institute. He left to go work for a private engineering firm. So sort of midway in the middle of this, after getting Parag going on this topic, we kind of tag teamed and worked together to develop this. And so we're really happy to give Parag a chance to defend it. I've told him to try to keep his presentation to about 35 minutes if he can. That's tall order for this much material, but he assures me that he's going to be close to that. When we're done with that, we'll open it up to the audience. And any questions from the outside folks? There's Kevin. Dr. Gu, how are you? So we'll open it up to the wider audience. And then after that, I think what we will do is something that Monica did in the previous defense, which was we will exit and go into a separate Microsoft Teams meeting. The committee will with Parag, and we'll ask our questions there, and we'll finalize over there. So Dr. Gu, I know, has a hard stop at 11, so we will try to perhaps, Parag, you can do your presentation, and we'll see how much time we have, but we'll let Dr. Gu go first with any questions that he might have. So with that, I'll turn it over to you.
Thank you, Dr. Usher. Let me share my screen. You see my screen, right?
Yes, we see it.
Thank you, Dr. Usher. Good morning, everyone. Good afternoon, good evening, wherever you are joining this presentation. Today, I'm going to talk about my research, high-density parking for autonomous vehicles. Let's get started. Parking is a daily problem. Whether we are going to work or attending a ball game, the first thing that comes into our mind is where we are going to park. In a common parking lot, we get a maximum of 67% space utilization, and remaining space goes to these driving lanes. And lanes must not be blocked for one simple reason. A blocked car might need to leave before the car that blocks it. However, autonomous vehicles give us an opportunity to overcome this problem and achieve higher parking density. Bosch collaborated with Mercedes and Ford to develop an automated parking lot where you can leave your car at a drop-off point. The parking lot has an autonomous controller which helps your car to find a parking spot. And whenever you are ready to leave, you call the car will come to the pickup point. No human needed, no civil infrastructure needed. In this research, we explore how to maximize such a parking lot. In this research, we explore how to maximize such a parking lot, and we ask 3 basic questions. These are basically 3 chapters of my dissertation. And next 35 minutes, I'm going to talk about all our findings, and there will be a discussion session at the end. And this talk, I'll keep it fairly on high level. However, if you have any question, I'd be happy to answer. So some of the researchers already worked on this high-density parking problem. The Ferreira et al. Was the first research group who introduced this high-density parking. They propose a parking lot design, parking car in parallel rows blocking each other. And they allocate some empty space on the entrance and exit so that cars can make their required maneuvers. So to improve this design takes a lot of movements. Timtner et al. Proposed a design where they introduce a perpendicular eye or driving lane so that the driving time, vehicle relocation time is minimized. Then another researcher, Benzoff et al., they propose to improve a traditional parking lot by adding an additional column of cars like this. And there's another research group, Nuri Najad. They propose a very similar design to Timtner et al., but in their design, they vary width of their driving lane with the depth of their vehicle parking lanes. So in all these research, all this literature, what is common is that they start with traditional row and aisle structure, and they look for the optimal parameters. But in this research, in my dissertation, we look for some very basic method. So we ask very basic question, like how many cars we can park in a parking lot without assuming any structure or any layout. So usually parking lots are rectangle and cars are also rectangle. So usually the high density parking can be considered as a rectangular packing problem, which is a very hard computational problem. In addition to that, we have to make sure that the cars can drive into and from a parking spot, which makes this problem even harder. To handle these difficulties, we consider parking lot as a grid, M rows and columns, and each car takes 2 cells in this grid, and cars can be parked either horizontally or vertically, and there is one exit entrance point on the lower left corner, and cars can make these 3 moves inside this parking lot. We also associate some cost associated with this movement so that we can compute the design performance later on. So we model the parking lot as a graph where each node represents as a parking lot layout and edge represent transition between 2 layouts. So observing the graph, we discover there exist 3 types of parking lot design. The first one, this one with which we call limited egress. Here we allow maximum number of cars. Cars completely block each other, and from this parking lot, car can leave only in last in first out sequence. Such a parking lot is commonly found in different special events like a concert or ball game. So, and the second type is the complete egress design, where we allow also, which is high dense, and also allow blocking inside the parking lot, but any car can leave by relocating other cars inside the parking lot. And the third type is the traditional, where there is no blocking, any car can leave at any time. So, and then we study how these cars are retrieved. For limited egress and traditional, the vehicle retrieval is very easy. In the limited egress, cars follow last in first out sequence, and then traditional, the cars can leave as there is no blocking. Anytime they can leave, we just count how many cells it move, and we assume that throughout this study that to move one cell it takes 1 time unit, and so. But for the retrieval in the complete egress design is not straightforward, because we have to relocate other cars. In other sense, we have to solve puzzles to find the vehicle retrieval process. So let's see how this process works. So for this layout, for each of these cars, we retrieve this like this way. These are the steps, shows how these vehicles can be retrieved. So you see that in this vehicle retrieval, we also use a graph search method to find this retrieval. And if you observe that for these five cars, these are the 5 nodes in the graph. So which is different than the graph we used earlier to generate the parking lot. So for search graph can be very large. However, we use a very efficient algorithm called A-star search, which helps to keep this graph in minimum size and find the optimal retrieval efficiently. So what A-star does, A-star ranks all the nodes according to a path cost, where G is the cost from initial node to a current node, and H is the a predicted cost from current node to the goal node. And Hart et al. They suggested that if H is non-decreasing in a path, then the A-star can give us the optimal retrieval or a shortest path. So for our parking lot design, we have proposed a single car heuristic as a H function here, and it can produce optimal result. I just want to explain how it works. For example, I want to retrieve this dark car from this parking lot, and as a single car heuristic, I place only 1 car in the same parking lot on the same location, and I count the number of moves it takes to retrieve, and this is our heuristic function. And as this single car heuristic follows a non-decreasing property, from A-star search we get the optimal result. So far we have worked on small problem. For example, we have solved 4x4 parking lot and 5x5, and you see that for 5x5 we have to explore 2.6 million nodes, and for larger parking lot it just explodes. So there should be some way we should incorporate designing large parking lots. So exploiting structure of the problem, we propose. Yes.
Parag, I have a question. 2 slides ago, please. 13.
Yes.
Yeah, but this is non-decreasing with respect to what?
Non-decreasing meaning, for example, from this point to the goal point, from this path, this value should not be decreasing. This value, the age value, it should always give us the total value of f should never increase. Well, then when A-star ranks all the nodes, then it gives us the optimal, or from short for small to large value.
I'm asking, you're saying that H of n is non-decreasing, right?
Mm-hmm.
That's non-decreasing with respect to n or some other thing?
Yes, non-decreasing from the n. Yes.
Okay, thank you.
N meaning the current state.
Yeah, I understand. Thank you.
Okay, so exploiting structure of the problem, we propose an algorithm we call puzzle-based parking algorithm. This puzzle-based parking algorithm, we create 3 zones inside the parking lot. In the zone 1, we park car horizontally, and then in the zone 2, we park car vertically, and in the zone 3, we apply our graph method to maximize parking capacity. So using this algorithm, we can compute the density of the both limited egress and complete egress parking lot using these expressions. Here, n is the number of rows and n is the number of columns. And we see how much a percent improvement we get in terms of density than the traditional parking lot. Usually when the mn is large, we'll get 50% improvement, which is theoretically maximum possible. However, we from our experimentation, we observed that when the parking lot size is small, this improvement can be much higher. So basically, that's why we suggest that this puzzle-based design should be very suitable for the urban setting. However, when the size of the parking lot increases, it becomes computationally difficult to find the optimal retrieval time. For example, this is a 5x5 parking lot with 10 cars, and this car takes 51 moves to retrieve, and computation time is almost 8 hours in a standard desktop computer. The long computation time is due to the heuristic we have used as a single car heuristic, because here we place only one car and it predicts only value of 8, which is really poor. Instead, if we improve our heuristic like this, like you'd see that this is a relaxed version of this our original layout, and we get better approximation, and now computation time reduces to a few minutes and we get exactly the same result. So using this improved heuristic, we can compute our retrieval time faster, but this heuristic does not promise the non-decreasing property, hence we do not get the optimal results. But it helps us to compute the retrieval time efficiently and very quick. So using this, we have computed retrieval time for up to 8x8 parking lot size, and we see that as size of the parking lot increases, it takes longer to retrieve. Especially these dark cars takes really long time to retrieve. And we observed that if we reduce this density by 20%, retrieval time improves by 60%. So far this is the first chapter where we answer how many cars we can park, and we have here I summarize our contribution. We have proposed a very high density parking lot design for autonomous vehicle, and we developed an exact algorithm to maximize parking capacity, and we have offered a heuristic solution for larger instances. And these results have been published in Transportation Research C. So far we have learned that we can maximize parking capacity, but as the parking size of the parking lot increases, it takes really long time to retrieve a vehicle. Even also the computation time also very difficult. So here we ask question, is there any way to improve the layout so that the total retrieval time is minimized? So let's try to understand this problem using as a small example. So we want to park 5 cars in a 4x4 parking lot, and we want to know what is the optimal organization of these 5 cars. So in a 4x4 parking lot, we can park 5 cars. Almost there are 2,000 unique configurations. This is the state space graph. So we have to explore each of these nodes in this graph to find out what is the optimal layout. So for example, if we start from this layout, which is generated by the puzzle-based parking algorithm, we compute retrieval time of each of these car, and we take mean, and we consider as a evaluation cost function to evaluate each of these nodes, and we explore all the entire state space, and we find this is the node this is the layout that minimizes vehicle retrieval time. So if we just compare for a small 5x5 4x4 parking lot with 5 cars, we can improve our parking lot design almost by 20%. However, that means that we should explore to find what is the best layout. So if we reflect that here what we have done, we have generated all possible state, and then we have computed retrieval cost of each state. And to compute retrieval time, we have used A* search just like earlier as a single car using the single car heuristic. And we also did the implemented the A star in parallel so that we can compute all the cars at a time to make the computation faster. However, generating all possible state is not an efficient approach. So we look for like, is there any structure available we can utilize it. So we see that in this graph where we generate all possible states, each of these nodes is generated making one of these moves. Therefore, if I know cost of one layout, I know that all the neighboring layout will be in the range of maximum move cost. So using this idea, we plot a heat map of that 4x4 parking lot with 5 cars. Here, light colored state meaning that it is low cost, and dark colored are high cost. Therefore, so we see that all the light colored nodes are adjacent to each other. So it is a very good candidate for a local search to find out the best optimal result. So here we chose to use simulated annealing algorithm to explore the state space instead of generating all possible state. Simulated annealing algorithm starts from an initial very high temperature, mimicking the metal cooling method, and at each iteration it checks whether the neighbor state is better than the current one. If yes, it chooses the neighbor state as a current state and it continues iteration. Otherwise, it chooses state randomly, and it continues iteration until the metal temperature goes down or it finds the optimal result. And here we integrate A star search inside the simulated annealing to compute the cost function. And then, as in the previous chapter, we noticed that A star search doesn't perform well with a single car heuristic for larger instances. So we propose a reinforcement learning approach to learn better heuristic. So basically, in the first chapter, we introduced an non-optimal heuristic, relaxing our structure, but that is only good for the algorithm developed by the puzzle-based parking layout. However, in this problem, we are going to see thousands of layouts, so we need an efficient approach. So what we do, we train a neural network and we generate random parking layouts, and we train a neural network to learn how many moves it takes to retrieve a car, and we use it as a heuristic function for the A star search. So combining all these simulated annealing and our reinforcement learning, we solve some of the problem from 3x3 to 6x6 parking lot up to 10 cars. So here we have all the optimal results. Here, for example, we have a 4x4 parking. This is a 4x4 parking lot with 5 cars, and optimal. It has mean retrieval cost is 11, and this blue colored means we have computed using the brute force method, which means it is optimal. And remaining layouts we have computed using the simulated annealing and the reinforcement learning method. And it is not optimal, but it is some good some good layout. We use that meta heuristic. So from this figure, we see that there are some layouts which are really good, which would not have imagined otherwise. However, computing these layouts are very expensive computationally. For example, to compute all those, it took us more than 2 months of computation time. So this is really expensive. However, what we observed that in a puzzle-based parking lot, we can optimize layouts, but it gives us it needs a lot of computation resources to come up with good layout. However, to check whether these layouts are good or not, we found very simple and useful approach. For example, we want to see whether the layouts are good or not. For example, it's a general trend that if we increase the number of cars in a parking lot, it takes longer to retrieve. So, for example, in a 4x4 parking lot, if we add number of cars, the retrieval time increases. So, our assumption, we get that the reducing number of cars, we can find a lower bound of optimal result, and we can check whether our result is good or not, and that we have found using the simulated annealing. Similarly, using the similar concept, if we add, for example, if we keep the number of cars constant and increase the area of the parking lot, the cost goes down. So using this idea, when number of cars is constant, we can use a smaller parking lot as an upper bound for the optimal result. So using these two ideas, the results we get using our meta heuristic, we see that these results are really good, and we compared these results with the results we find with the puzzle-based parking layout, and we see that in terms of retrieval time, all the layouts are on average we can improve the layouts more than by 20%. So far in this chapter, we have developed models to improve puzzle-based parking layout, which reduces vehicle retrieval time, and we have also presented analytical insight to generate efficient layout, and we have prepared a manuscript to submit in a journal, and hopefully we're going to submit it very soon. And then so far we have learned how to maximize parking capacity, and we have learned we can minimize the retrieval time. However, minimizing retrieval time is a very difficult computational problem. So is there any way we can utilize this high density parking concept in the large scale? So from this idea, we see that the traditional parking lot is designed as a row and aisle structure. Like, how about you can apply the same approach to design a large parking lot. For example, like this, we combine small blocks of puzzle-based design, and we place it as a row and aisle pattern, and we can generate parking layout. Such parking lots we call sublot. In the sublot, there are some differences from the puzzle-based design we developed earlier. In the earlier, we had exit entries on the lower left corner, but in the sublot design, cars leave or enter from the side, and this is why the retrieval time is very quick and computation is very fast. So let's see how we can design a sublot parking lot. So for a sublot, we identify a block, a small chunk, and then we stack it to the entire width, and then we repeat this column entire length. This is how we can generate the very simple sublot design parking lot. However, we may have some leftover space like this on the bottom on the right. So what we do in the smaller space, we fit smaller sublot just like this, and then we repeat it along the length. And when we have some leftover space along the length, we fit the traditional parking lot just like this. So using this, we can design a complete sublot. And then to simplify our computation, we assume that the parking lot is dead end, is closed from one end, and the cars enter, exit on the lower side, and the exit entry is located in the center location. So from this, we can easily develop a mathematical formulation to compute the density of both traditional and sublot design. Here, M is the number of rows in a sublot and number of columns, and E is the number of empty cells in a sublot. And as like earlier, we can compute retrieval time using the A-star search, and retrieval in the sublot design, it follows two steps. First, we have to retrieve from the sublot, and then from sublot, it follows the driving lane and it goes to the exit point. And for the traditional design, we only have this traditional travel. So with this, we have the model to compute density, and we have the model to compute the retrieval time. We perform a set of experiments to understand which size of sublot perform well in terms of density and retrieval time. So to do this experiment, we chose different parking lot capacity of traditional parking lot capacity of 50 to 2,000. We chose the parking lot shape, where shape meaning width over length from 0.1 to 2.0. And for sublot, we chose a number of rows from 3 to 10 and a number of columns from 3 to 6. And using performing the experiment, we first study the percent improvement in density with respect to sublot area. Here we plot improvement in density with respect to sublot area for various capacity of the parking lot. So, and we see that as the sublot area increases, the improvement increases, which is we guessed from the beginning. This is what it should happen. And obviously, for the larger lot size, this improvement is much higher. For example, when the parking lot is 2,000, and if we use a sublot with the area of 60, we can achieve 50%. We can add 50% more car in a sublot design. For example, for 50% becomes 300 more cars. So that's a huge achievement. For a large parking lot, we can add almost 300 car using our sublot design when the area is 10 by 6. However, we should notice that we can achieve.
I have a question, Parag.
Yeah, sure.
Yeah, the previous slide, please.
This one?
Yeah, did you say 50% improvement?
15%, sorry.
Thank you.
So theoretically, we can go for 50. What Dr. Yu is saying, that we can go for 50% when the number of subplot, number of rows and columns are high. We can reach up to 50%. But we computed up to only M10 and 6. So we achieved 15%, and we just compare here that from using only 6 columns, we could have reached 25% improvement in terms of density when we have large number of M. And we also noticed that subplot with column 4 we should only use when it is when the number of rows is greater than 10. Otherwise, it doesn't give us any benefit in compared to the traditional parking lot. So here we see that it is possible to achieve almost 100% density in a sublot using this sublot design. However, computation time is really long, as we discussed earlier. The retrieval time is also long, and both the computation time is long. So here we have chosen a few sublot which are good in terms of density and retrieval time. For example, here it shows a 10:3 parking lot, and number on each car shows how many moves it takes, and this is the mean retrieval time for each parking lot. And the maximum which we selected, 10:6 parking lot, and mean retrieval time is approximately 15, and computation time is around 6 hours for this. Now, then we compute the travel inside the driving lane. Here we plot mean travel in the driving lane with respect to parking lot shape for various parking lot capacity, and we also plot for various parking lot the various sublot size. And we see that the parking lot shape has a really significant impact on travel inside the driving lane. Usually, when the parking lot shape is 0.5, it reduces the travel time inside any size of parking lot. And another observation is that as the size of the parking lot increases, it takes long time to retrieve or long travel inside the driving lane. And then the last observation from this figure is that the travel time inside a driving lane for a sublot is same as the travel time inside a traditional parking lot. So if we compare our design with traditional parking lot, and only difference is the travel inside the sublot. So if we can design an efficient sublot, we can get a very good result from our sublot design. So now we present a case study using our results. What do we have? So this is a this is a parking lot from our Cardinal Stadium, and this stadium can accommodate almost 1,300 cars, and mean retrieval time is 42 seconds. And here we are going to apply our sublot design to see how much improvement we can get. So first we use the 10:6 sublot, and we get this layout, and we can achieve almost 15% improvement in terms of density as expected. However, retrieval time also increases as expected, but the thing is, this will be an automated parking lot. As a human, we do not need to walk inside this parking lot. Rather, we just need to call the car, and the car will come to us. So all we have to do, we have to program in our phone so that the car will come. Our phone will call the car a few seconds earlier. That's it. So there's another interesting. Another interesting design would be a class-based design where we place a smaller sublot located near the exit entrance point, and the denser larger goes in the far area. So in this way, the cars which needs to stay only for short duration, we can park these here, and we can get almost 10% improvement in terms of density. So here I summarize my contributions. So in this third chapter, we proposed a modular design to design a large parking lot, and we also developed some guidelines in terms of density and retrieval time to get best performance. So if we summarize overall contribution from this dissertation, we have introduced a puzzle-based parking algorithm or puzzle-based parking lot design, which can give us very high density, and we develop computation models which can represent puzzle-based design, and also we can investigate optimal results. And we proposed a modular design to design large parking lot where we integrate small puzzle-based sublots. So a good dissertation not only solves question, it also brings new solutions, new problems as well. So in this this particular design problem that we have studied, it is only very early phase research. So there are many, we have to do a lot of stuff to make it real. For example, we should integrate various car size in the parking lot. Then another interesting research should be usually in the urban area, parking lot comes in multi-floor. So how we should integrate this puzzle is designed, the multi-floor. Then obviously a completely different stream of research could be designing the control algorithms for those controllers. And then very useful research would be that there be the mixing autonomous and traditional vehicles, and obviously studying the pricing scheme for the pricing scheme would be another interesting research stream for this research. So far we have published a paper at Transportation Research 3, and we have 2 more drafts ready, and we are targeting the same journal again. We have published in a few conferences. We presented at IAC and Informs outlets last few years. And other than research, last 5 years, I have worked on different projects. For example, at Lodi, I worked on one of the projects at Houston Johnson, and which was really successful, and I learned a lot. And last 2 semesters, I worked with Dr. Gentili and a few other professors from our department to develop the career path seminar series, and it was really helpful for me and also for other students, I hope. And finally, I want to thank everyone for attending this my defense talk, and I'm really grateful, Allah Almighty, giving me this opportunity to work on my dissertation and finishing it. I want to thank Kevin Liu for his excellent guidance, brilliant ideas. I want to thank John Usher for helping me in the really difficult time. I appreciate Dr. Gentili for all the support and all the helps regarding in terms of my dissertation, and also as a Lodi RA, she helped me a lot. And I want to thank Dr. Yampolskiy for carefully listening my questions and replying, giving some very careful comments. I met amazing people last 5 years. I want to thank you all. I want to thank my family members, and finally, I want to thank all the funding sources for my research. So with this, I want to I'm open to take questions. Thank you very much.
All right. Well, that was 35 minutes. I'm impressed. When he said 35, he meant 35. So
yes, yeah.
You're getting applause. Okay, so it sounds like we have a little bit of time. Let's open it up to the audience quickly and see if there are any questions from the folks who are not on the committee. This is usually when the presenter plants a softball question with one of the attendees to ask to make them look good, but apparently Parag did not do that. Anybody? Any questions?
I think Dr. Gu missed. We have Niels Boyson in the audience. We can talk later on.
Yeah.
I just want to make a comment here.
If you
can see me, my camera just keeps misbehaving. There you go. Good seeing everybody. Hey, Parag, great work.
Thank you,
Kevin. Great work. And I attended your proposal defense, and it was fabulous work back then, and it's even better with sublots. Congratulations on all the publications, and I just want to applaud you for your grit, perseverance through different times in your PhD. And I'm sure that life has taught you a lot of lessons, and Dr. Kevin Gu and Dr. Usher, with their experience in research and other life lessons, I'm sure you have come out as a much different individual compared to what you entered in. So I hope, that is my hope. Again, it depends on your nod, yes or nay, but I just want to congratulate you on that. And you, Mohsen, Meena, some of the star PhD students are really great role models for our current and future PhD students. So we are gonna keep you in mind and keep in touch with us. But for now, I don't have any questions. My best wishes for the next 1 hour that you would have to face the bandwagon, and I hope you can come out victorious.
Thank you. Thank you.
All right. Any questions from anybody in the other audience? Okay. Let me throw this. Oh, go ahead.
So Parag, again, congratulations for the wonderful presentation.
Thank you.
I had one question where you had the heat map. Why
Sure.
is that not completely symmetrical?
Oh yeah. Let me go back. So we basically we use only one entrance exit. So this is symmetrical, but we could not omit those symmetrical because if you notice in each parking lot we have exit only one side. If we had exit on the other side, we could remove those parts, but it's due to our assumptions. We assume that the entrance exit will be on the bottom side, so that's why we could not remove all those symmetries.
Got you. Okay, thanks.
Welcome.
Okay, let me throw this out to the committee for a second. I know, Monica, in Mohsen's defense, you had us move to another room, which we could do as a committee for our discussions, but I'll just throw it out to the committee now. If you want to ask questions now to him, I'm fine with that, and we can move over to that for our deliberations rather than asking everyone to leave. But I'm open to suggestions on how to proceed at this point. You're welcome to ask committee questions at this point, or we can move over into the other Microsoft Teams meeting.
John, before we answer that question, I want to just insert, I was just mousing over all of the attendees. It's a veritable who's who of interesting people.
Really?
I just want to thank everyone who attended, many of people that I know and are friends. So hello to all of you. I don't expect you to respond, by the way. That would be weird. But anyway, so thanks for attending Parag's defense. This is just great. Appreciate it.
Great support.
Yeah.
Okay, then
Yeah,
Monica?
John, yeah, I would suggest that we actually go in a separate meeting room just to ask Parag question and let him feel
Okay.
comfortable talking with us, and then we can also ask Parag to leave and we can deliberate among all of us and come back
Right.
here.
And then we can come back here, so
Yeah.
all the friends and those
So they
that
can
are
stay
interested you can keep yourselves logged on to this meeting, and then when he comes back, you'll learn the decision at that point. So, all right. So I emailed the invitation for the other room to folks. Hopefully you've got it. So I guess we'll exit now. We'll go back over to that other room for deliberation. All right.
Yes.
Just the committee. Thanks.
See you, everybody.
Kevin,
Good luck, Parag.
you're muted, Kevin.
Yeah, this will take me 1 minute. I need to forward the invite to this computer. So I'll be a second late.
Sure. No problem. No problem.